Welcome all of you. Today this is the ninth session on a problem solving session, a kind of problem solving session. So today we'll discuss some problem based on the course that we are learning right now, the essential of the oxidation reduction and carbon-carbon bond formation reactions and applications in the organic synthesis. Right. So we have covered several topics in which is in the which are covered in this course from the beginning, and this is the week 9. So up to now we have seen already many the oxidation kind of reactions, oxidation reactions. Also, we have seen some stereo selective oxidation reaction. In terms of the, you have seen some examples of the epoxidation reaction, right? Or dihydroxylation reactions in the stereoselective manner. Further, we have also seen some reduction reaction and followed by some stereoselective reduction reactions. And as we are learning in the topic that is the in this course, like the carbon-carbon bond formation reaction. So today we'll see some different kind of carbon-carbon bond formation reaction, particularly based on the enolate chemistry. And so if you have any doubt regarding the topic which are covered by the professor in this week 9, so you can let me know anytime. So in between. So we'll start this session. So we have already waited for 5 minutes to join some participants. So if there are no many more participants are coming, then we'll gonna start directly to solve the question that we have selected for this work. So let's start with the simple question. So if you have some keto compound and let's say this is the simplest, let's take this simplest example, and we have to do the reaction in which we have to we want to add some, let's say for a for our convenience, and just let we want to add the methyl group at the alpha position to this. So what are the different reaction conditions that we can use for the such let's say a carbon bond formation? In this one, let's say we have some reagent like the methyl iodide, and this is the kind of electrophile, and this is the nucleophile in this case, right? Electrophilic in nature, and this iodine is nucleophilic nature in this case. Or also you can say this the carbon is delta positive in nature, and this iodine is delta negative in nature. So the bond polarity is in this manner. So the iodine is have the more electron density from this carbon-carbon bond, right? So if you want to do this reaction and want to perform the alkylation, so what is the reaction condition in this case? So if you think about the adding some base, so the base can form a anion at this position, right? So if you add a base, what happens? It forms the anion and which get the stability. These anions get the stability by this kind of O minus this kind of enolate formation, right? That's why the acid this proton which is at the alpha positions, they are very easily get these are very active protons. By treating with the base, this can easily abstract one proton. And what happens when it treated with the when it comes in contact with the methyl iodide? So it forms the alpha. This enolate gain goes back to the ground. So the formation double bond, and then by this carbon, this attacks on the methyl. So it will give this product. So, but if you see the reaction, so we are not going to add only one molecule of this one, right? So in the reaction mixture, there are multiple molecules of the methyl iodide also present. Also, the multiple molecules of the base also present, and as well as the starting materials is also in the present multiple molecules. So what happens? So this product form upon first methylation, this is more active than this starting material itself. Why? This is because the stability that we get upon abstracting the another proton. So upon abstracting the another proton, we able to form this enolate, and which has the more stable because it is a quaternary enolate, because both the this is already substituted methyl, right? So it is quaternary inlet, and this double bond, if you see the double bond, this double bond is more stable as compared to the bond which is formed by using this here was the hydrogen, right? So among this bond. So that's why the second reaction prefer to go on such carbon. And here what happens, the multiple uh, what you can say, uh, multiple reaction occurs on the same starting metal, multiple steps. So it gives as a result it gives such compounds, right? So this reaction is not able to control. That's the reason there is a issue with such a simple synthetic transformation. We can't directly add the directly one equal to sorry, base as well as the uh, what is the reagent that we want to attach here, so that that is not experimentally feasible. So that's why we need to use different conditions, and particularly that we'll discuss today's lecture. So here is the first example, and in which I have given. So the base here in this case used is the lithium diisopropylamine or LiHMDS. So with this base, and we need, if you add the MnCl2 or MnBr2, it gives the formation of this inulate, and when you add the methyl iodide, it gives the 76% of the product, that is the monoalkylated one. But if you not use these MnCl2 or MnBr2, in that case, what happens? We get a mixture of products in which this is the first product, and again the mixture of this product. Again, there is a possibility of this product, and so on. So there is possibility of too many products are there, and also the product which contain the. So this is how too many products are getting formed if you don't use the this kind of chelate formation, that is MnCl2 and this kind of additive. So that's why this although the reaction looks simple, quite simple, but this is not the case in case of such kind of active methyl when you have such systems. So another condition here is the addition of the QS, which is the KOH, and we use the tetrabutyl ammonium bromide, right? When you use this one, it gives the selectively alkylated the alpha positions, which is addition to the phenyl. Why this is? This alpha position is first thing is the more active compared to this one, because the inulate form in this case was the is the this phenyl, right? This is the inulate gets form O minus and methyl. So this double bond, which is the tertiary double bond, and it has the higher stability compared to the double bond, which is says to this double bond, very stable. So that's why the inulate form is the one which is the tertiary inulate. And also this tetrabutyl what it does do, it does like it stabilize the inulate. So this inlet form gets some sort of stability because of this additive, and as a result we get some the selection of this monomethylated product about 100% without formation of this one. So it goes, the reaction works very selectively in this case. So if you look at the some if you have some starting, and if you look at the multiple condition, so if you use the base like the LDA and the in the DME solvent at minus 70 degrees Celsius, we get the formation of this inulate only in 1%, but the inulate form, this is the about 99%. So it get kinetic controls over the thermodynamics, right? So that's why the kinetic product forms a more major amount. Thermodynamic is the kinetic product means the abstraction of proton, which proton is more easy. That product is the kinetic product in this case, and the thermodynamic product is the how this anion inulate form, which is the stable. That the stable inulate one was the one is the thermodynamic stable product. So the kinetic is mainly deals with the rate determining step, and in this case, which is the rate determining step, the steps in which the abstraction of proton takes place. So the from this one to the inlet formation, that step is the kinetic steps. So that's why kinetically stable or kinetic product is the kinetically controlled reaction in which the first proton abstraction proton, which is the the easier one, which abstracts the preferentially, right? So that's why the inlet, which is the tertiary inlet, is getting from in the kinetic control one. But if you look at the thermodynamic control at that time, the more stable inlet that is going to form. So if you add the LDA at minus 70 degrees Celsius, the reaction goes via kinetic control, and we get the inlet, which is the tertiary. But if you add uh, the triphenyl, that is the carbon which has the triphenyl, uh, three phenyls, as well as and with the lithium. So, and at the minus 70 degrees Celsius, here also the kinetic product is getting formed. But if you do the perform reaction at with the same one at the room temperature, in that case the thermodynamic control inlet getting formed, which is the stable inlet. Further, if you add the third butoxide, potassium third butoxide in the butanol solvent, the inlet form, which is the thermodynamically stable inlet getting formed. So you can see here the difference between these two. Let's say if you look at these two minus 78, at that time kinetically controlled product getting formed, and at room temperature the inlet form, which is a thermodynamically stable, and also the product also getting in the same manner, right? After that, if you add any electrophile, the reaction takes place via it adds to the electrophile, right? So that's why the product form, which is the electrophile here, in this case the product form which get the electrophile at this position. Further, the next reaction, if you see here, if you add the LD at minus 78 degrees Celsius, again here, in this case, the inlet, because sorry, the inlet form, which is the less stable, the thermodynamic stable inlet is not getting formed, but the inlet by using the reaction go via kinetical controlled manner, because this perform at the minus 70 degrees Celsius. Further, if you look at the another example, another base, the triphenyl methyl lithium. In that case, the thermodynamic control inlet getting formed preferentially, which is around 87%. So depends upon what condition we are using. The reaction goes via thermodynamic control or the kinetic control. So if you look at if you want to do now again the first example, if you want to get the selectively mono alkylation, what we can do, what is the steps involved here. So we require to add the base. Upon adding the base, you can see here the first it abstracts the proton, it forms inlet here, right? And it get forms converted into the corresponding inlet. That step we have already seen. And then this is the electrophile. It directly attacks on the carbonyl carbon, right? And it gives the C double bond O OET. Further, again, second equivalent of the base, if you add, at that time, the preferentially abstract this proton, because now this proton is the active proton, more active, and preferentially, selectively, this proton is getting abstract, and it gives the monomethylated product at this position, right? Although it involves the too many steps. So the methylation occurs selectively at this position. So this reaction works 100 give the 100% 100% works at only at selectively reaction goes at the carbon which is attached to the ester group, and further upon heating in the acidic condition or a salt like LiCl and the DME solvent, it gives our product. So to convert this to this, so you can see these many steps are involved. So to get the selective monomethylation, so we have to perform first, second, and the third three steps. Then we will get only monomethylated as a selective product. Further, in this case also, the stereochemistry comes again. So if you want to get the very stereoselective addition of this methyl, then there are different conditions or stereoselective addition of the carbon bond. So this we have formed this carbon-carbon bond, right? In this case, so we are able to form this carbon-carbon bond. But if you want to get add this carbon bond stereoselectively, so now the picture comes the further the organocatalysis or the asymmetric catalysis, that kind of reaction requires, and we need some sort of sterically controlled either starting material or the reaction condition in which the uh, use of some stereo chiral ligands or the use of chiral catalysts that are or maybe the starting itself is the chiral. So if you look at the if you go move slowly to the chiral one versions, so if you have some such starting material in which you can see the orientation of the bonds, so this is the starting one. And if you want to do the stereo selectively, if you look at the base, so the in this case uh, there are two different positions available, right? So this is the one, the position, both hydrogens are equivalent, and this is the another second, so in which the hydrogen attached to the alpha carbon, which is attached again to the another ring. So now in this case, if you add normal base and methyl iodide, base like potassium tert-butoxide, the methylation occurs at the position here, because what happens in this case, the proton which is attached to the which is attached to the two ring, let's say this is the A and the B, and this proton abstraction is get difficult in this case because the tert-butoxide is quite bulkier base. So the major product forms is the this one, in which the potassium tert-butoxide simply abstract the proton, which is the easy to abstract, and it forms a enolate in this manner. So the enolate form uh, is this enolate getting form, and further upon addition of methyl iodide, so it gives the product in which the methylation this position, right? But if you want to do methylation on this one, which is shown here in the red one, if you want to do the methylation at this point, then there are different protocols that we need to use. So, what is protocol here to do the methylation at this position instead of this? So, what we can do, the base we need to use this sodium tert-butox as seen earlier example, the sodium ethoxide, and with the HCO2 ET, that is this is the so this is the OET, right? So this is the electrophile. This is the source of electrophile. So what happens? Uh, Not it's not like earlier case. So that also you can use. So if you use this one, so what we will get? The first step we can get selectively, but this is the in this case not like earlier case that we have used here, like the in this case what we have used, we have added C double bond O ET, right? That's the we have used in earlier cases. So we have added the this additional ester followed by the methylation, and again we have cleaved the ester to get the mono methylated. But in this case, the different protocol have is used. We have added this normal mild base like sodium ethoxide, and it abstracts the proton, which is the obviously this proton is first getting abstract, followed by the electrophile, which is the HC double bond ET. That's the this is the ester, and BUSH and the TSOH. In that case, it forms this is the example of the name reaction. So this is the question for you. So which is the name of this reaction? So you can find out what is the name of reaction. Yeah, but in between, it forms such C double bond C SBU. That's the product form. And now, if you abstract the proton using the tert oxide and the methyl iode and treated that enolate with the, it forms the enolate, which is in between the both. So this the enolate getting formed, and upon addition of the methyl iodide, which is again present in the reaction, so it gives the methylated at the position which is attached to the A ring, right? So in this manner, you can get the methylation at that position. And again, now we have to cleave this bond. So for that, there is a condition like you need to add the base, potassium hydroxide, and water in the ethylene glycol. And upon reflux, it gives the cleavage of this bond and it gives the hydrogen at this position. So you can see in this manner, you get the good major amount of this methylation at the position, which is let's say at the A position. But if you want to do the methylation at the B position, then we have to perform this much. The first, second, and the three and four steps are involved. So to perform the methylation at selective position, the different protocols are required to use. So if you see some examples of how the reaction works at what different conditions. So this is the first example in which you can see added this is isopropyl magnesium bromide. So this is kind of a base, right? And the electrophile here we have, this is the Ma3SiCl, the silyl chloride. So upon addition of the silyl chloride, what happens? The this is the base which abstracts the proton, and it abstracts the proton selectively. This proton abstract followed by the silyl to form, which is 97% is getting formed. So in this case, it forms 97%. But if you use the different ways like the LDA, it forms this enolate, which is in 99%. So you can see the difference in the enolate formation. If you want to form a quaternary enolate, that case we can use this isopropyl MGBr, right? NMGBr. And if you want to use if you want to get this tertiary enolate, in that case, we can simply use the LDA. Further, the another condition is the use of the methyl lithium. If you use the methyl lithium, it forms the quaternary enolate, and this is the reaction example of one of the reaction. You can use the methyl lithium. It abstracts the proton, forms a quaternary quaternary enolate, which is get stabilized by the lithium. And further, upon addition with the electrophile source, so this is the electrophile source. So phenyl CH2 Br, right? It gives the formation of the product in 87%, which is comes from this quaternary enolate, and the enolate the product which comes from the tertiary enolate product, and this is the quaternary enolate product. The tertiary enolate product also getting formed, which is very minor, about 7%. So this product is getting formed. Another example here is the example of the if alpha beta unsaturated double bond, right? Ketone. So here we have the alpha beta unsaturated saturated ketone. What does it form? Upon abstraction of the proton with the LDA, it forms this enolate, and upon treating with the methyl silyl chloride, so trimethyl silyl chloride, so it gives this silane. This is the product, and when you use the any kind of further in this case we have this is the source of electrophile in ZnBr2. So this ZnBr2 cleaves this OSI bond, used to cleave this OSI bond, and it forms an enolate. This enolate then goes here and attack to the methyl. So you can see here, this was the our initial starting, and upon we have formed this new double, sorry, carbon carbon bond here, right? So we have selectively abstract the proton of from this condition and attach that proton to the this phenyl bromide, right? So upon on this one, so this new carbon bond getting formed with these steps. Thus, another example here is the addition of triethylsilyl hydrogen. So use of this triethylsilyl hydrogen and 5 mole percent of this sodium based catalyst at 50 degrees Celsius. So uh, upon reaction, it gives this inlet formation. So what happens in this case? This triethylsilyl hydrogen gives a source of proton. So upon addition of the this catalyst, so it forms the shifting or double bond takes place around this one, right? So this is the condition that you can remember. So in which the use of this metal catalyst to get the this inlet, which was not the case in the previous one, right? So in this previous one, uh, we have formed inlet in the this manner, which is the available CH2 H. This proton is getting abstracted, but in this case, although there are two protons are available, however, in this condition, we get the inlet as mentioned here. So, if you look at some of the examples of such chemistry, so this is the simple one of the examples. And if you look at the condition they have used, is the this is the 27. The this is the starting material, and upon treating with our ketone, so what is formed? It gives the the lone pair of nitrogen get in all the conjugation followed by the attack, this nucleophilic attack at this fourth position. 1,4 addition takes place in this case. The fourth position and we get a inlet in this manner, and this inlet further get rearranges because which is in the thermodynamic equilibrium. So it get forms from one inlet to another inlet is getting formed. So this just the transfer of double bond from this case here to here. So what else happens here? The another molecule abstracts the proton, and so this is how it abstracts the proton of the some another the same another molecule, the proton which is available at here, and it forms the anion here, and again it forms the inlet. So this is the inlet getting from, and which is on upon addition, it attacks in this manner, and we get a product which is the mesimbrine. So this is the one of the natural product, and this mesimbrine get forms uh, just by performing. This is the first starting, and this another starting, and this is the just a solvent, right? Ethylene glycol solvent at 120 degrees Celsius, about 56% of yield we get in this reaction. So this is also one of the carbon-carbon formation reaction, and it also involves some uh, beautiful enolate-based chemistry. So as mentioned earlier, so as of now, what we have did like the form the carbon-carbon bond, but how we can control this? Uh, uh, we have reduced selectively control as of now the carbon-carbon bond formation. Now the question come how we can stereo selectively control this carbon-carbon bond formation, right? So this is the one example that I have shown here. And if you look at this example, so you can see, uh, let's say we have the starting and starting like that's the OH or OET, right? OH, let's say. And if you want to add this convert this into the this one methyl group, let's say. But what we want in this case, we want a stereoselective this type, right? So if you want to perform the stereoselective manner, let's say we want to perform this methyl. Uh, if you think this methyl should be directing the upward, or if you want to perform any, this group should be directing this, instead of methyl you can take generalized example like the R group directing downward. So in that case, uh, how we can proceed? So we can use this kind of chiral auxiliary type of approach. So chiral auxiliary, right? So the chiral auxiliary is like the what we do, we add some, let's say this is our the starting, we add some external auxiliary, so it forms S plus a complex, and this S plus A, because of the stereochemistry of this A, the addition takes place on this, the starting and the auxiliary complex, in the stereoselective manner. So whether this manner or this manner, so the addition takes place on the stereoselective manner. So and further upon reaction, we can finally cleave that or the break that bond which involve between the the S and A, that is the starting and the auxiliary, and we can remove the auxiliary and we get the product, that desired product. So in this case, one example here is the this the chiral auxiliary that have been added. So one first converted this material into the this one. So this is just a chiral auxiliary we have added by using the this ester, sorry, the acid. We have just added the acid amide coupling by using the acid amide coupling, right? So I added this auxiliary to this one. Then we have added the abstracted the proton by using the LDA, and which proton is getting abstracted now? This is the proton which is getting abstracted. And because in the auxiliary, you can see in the auxiliary, what does lithium do? Lithium forms a chelate between this one, lithium, right? So this lithium goes in between, and now this entire system is getting uh, uh, buckled together, right? The entire system is now, you can see here. So because of this chelate formation, this entire system is stay stationary in this manner. And when you abstract the proton, it forms an inolate here, and this inolate then stereoselectively attack on the this electrophile. So in this case, the allyl bromide. So it attacks the aryl bromide, and since this entire group is directing downward, so the new bond comes. So it attacks. So let's say this is entire this group is below the plane. So the new group coming, it should become from the above the plane. And this you can see here, the new bond formation and this new bond form. So this bond is directing upward. So the in the chiral auxiliary, what we have the bulkier group which is directing downward. That's why the this electrophile doesn't comes or doesn't approaches the nucleophile from the downside. That's why the the electrophile which is present on the top side, this nucleophile attacks on that one and it forms a bond, and you can see the new bond forms which is directing down upward. So this is how we can control a stereochemistry while the carbon-carbon bond formation. This is the very simple and the basic example of the chiral auxiliary, and you can see how beautifully we have able to about 98% of the product form which is in which the this auxiliary is this entire group is attached on the beta position, right? And if you look at the diastereomeric ratio, the diastereomeric ratio of this product is 96%. You can see how and what we have did, only added this chiral auxiliary to the starting one. And if you want to get the product final product, we just need to just cleave this. We can just cleave this group, and we get the our required product in hand. So upon deprotection, we get the product in hand. So that's the use of the chiral auxiliary. So another example you can see here. In this case, what we have used the chiral auxiliary. So this is the chiral auxiliary, and in this case, it abstracts the proton, it forms the invalid at this position and negative charge at this one. And when it get the negative charge at this position, since these both group are directing upward, the final product form in which the new carbon-carbon bond forms, which is directing downwards, right? Because this nucleophile cannot approach from the top side, because now on the top side, what are the group bulkier group present? So this methyl and the phenyl group are present on the top side. So whatever the new group or the neighboring at molecules come, they comes to the neighbor in the vicinity to form a bond will be come from the downside. And you can see the stereochemistry how we get the stereochemistry directing downward. And this also in this case also the direction ratio is about 96%. So this is the one of the classical example of the chiral auxiliary or chiral auxiliary, use of chiral auxiliary and to get the stereoselective carbon-carbon bond formation. So I hope you got this point of the chiral auxiliary. So here are some examples in which you can see. So here, if you want to perform this to this, right? So this is the starting A to the product B. If you want to perform this reaction, and we want the methylation at this position, right? If you want to methylation at this position, and that also in the stereoselective manner, then what are the steps involved for this conversion? So this is the first step. So the first step is the PCC. What does PCC do? It converts this alcohol to the corresponding aldehyde and probably convert into the acid, and we have then added this chiral auxiliary, that is the acid amide coupling. It forms this. We have added the chiral auxiliary in the over this first step, and then we have what we have did. Then we have added this the base and in the THF. So what this does, it abstracts the proton, and now you can see this in the auxiliary, this CH2 pH group directly downward. That's the reason this methyl group will be come at the from the top, and upon treating with the LiBH4, this entire chiral auxiliary get cleaves, and it gives the final functional group the this entire chiral auxiliary, and this keto group, the carbonyl group get reduces. This carlog will get breaks first step, and then this form aldehyde get reduces to the corresponding alcohol. So by using this simple one reagent, so this is how uh, we can able to convert these. We can able to convert this compound to this one just by adding the first addition of the chiral auxiliary. The first step is second step is the addition of or formation of uh, carbon-carbon bond in stereochemical fashion, stereoselective here, stereoselective fashion, right? So this bond formation it takes place in the stereoselective fashion, stereoselective manner, and which is obviously controlled by the chiral auxiliary, right? And the third step is removal of chiral auxiliary. So this is how within the these three step conversion we can able to get this methyl, and so that's the required product. We can do this one, right? So although there are multiple steps involved, but we can able to convert this a chiral molecule into the required chirality by using this type of conversion, right? So that's already seen. We can able to do the how the stereosemic conversion. This is just the summary of this chirality. Just I have put some slides and which are taken from the presentation, and you can see uh, although there are two different type of proton available. Now, if you want to perform uh, add this either this one or this one catalyst, if you want to make which is obviously the enantiomers of each other. So what we can use, like the chiral catalyst we can use, or chiral catalyst reaction condition, or as you seen earlier, the use of the chiral auxiliary, that also you can use. Again, there is the use of the asymmetric aldol reaction, and this asymmetric aldol reaction is also one of the uh, classical reaction in which the use of proline based catalyst are used. So what does happens in this case? So this proline, what it do? The proline attacks on this ketone, it forms the imine intermediate, and upon formation of this imine, it gives the abstraction of the proton takes place and followed by the cyclization here. So we can get so in this case the imine forms and followed by the addition across the. So in this case there are multiple uh, sites are available, right? So this is, but if you look at this side, this is the very preferable side because there is less steric crowd. So that's the reason this it forms a imine at this carbonyl, and it forms the imine in the pan fashion like the CH2. C double OH, right? And this, let's say this the entire group, right? So the group that I have represented here, uh, as it has the positive charge, what it happen? The proton which is present at here, so it forms in this manner, and it forms a enolate, and which this enolate is the getting form, right? And this enolate is further than uh, this CH2 that we have seen. So the CH2 here, which attacks on the carbonyl carbon, and as a result, we get which carbonyl carbon? So the carbonyl carbon which is here. So that's this is the carbonyl carbon to which it attacks, and we get the product. So this is the example of the use of the L-protein. So we'll see more example in the uh, next few slides. So as like the earlier cases, so as seen earlier, so how we can use the chiral auxiliary to get the stereoselective carbon-carbon bond formation. But if you want to use the, but we want to form again the carbon-carbon bond between the intermolecular fashion. So this is the one of the approach in which the use of the L-proline based catalyst, organocatalyst is getting used. So here is the example or another example, which is the proline catalyzed asymmetric intermolecular aldol reactions. So in this type of aldol in this example, the proline forms a enolate, so preferentially react with the aldehyde. So if you look at the reactivity between the this is the aldehyde, right? And the another one example is the ketone. So this aldehyde is more reactive towards this imine. So that's why uh, it forms a such eno enolate, right? So the iminium ion. So there will be, and upon abstraction of the proton, which is here. So upon abstraction of proton, this proton, it get converted into the, so this here there is COOH. Upon abstraction of proton, it forms, so this proton is get converted into the, so the bond pair can get into the carbon-carbon double bond formation, and this positive charge get neutralized. So it forms this intermediate, and further this entire group attacks on the ketone, and again upon followed by the first the step is the attack on the ketone, and the second step is the second step is the further abstraction of the proton, which is obviously from the solvent. So it gives the product, and because of the stereochemistry of the COOH group, so we get the product which is in the about 96% enantiomeric excess. So the this is how we can use the proline based catalyst for the enantioselective reactions, and this is the example of this intermolecular aldol reaction. Earlier example was the intramolecular. This is the intermolecular. So the difference is just simple. Intramolecular, that is the occurs among within a same molecule, and this is occurs in the different molecule. And also you can see here the startings, the reactivity difference drives this reaction. So this the one first reagent is the aldehyde and the second was the ketone. So this uh, preferentially the aldehyde more reactive to forms the imine, and which again then the reaction takes place in the aldol type reaction, and it gives the product. So what are such examples are available for the organocatalysis? So there are, if you look at the toolbox, so these are our generic activation modes. So the covalent activation mode and the non-covalent activation mode. So if you look at the covalent, there is enamine based catalyst that's I've seen earlier. So this is the enamine, and this enamine based catalyst we can use. Further, the iminium catalysis. So iminium is just like the, as seen, we got here the positive charge, right? So that's the iminium based catalyst. Further is the phosphine based. So we know there are multiple phosphines are available. They are chiral in nature, chiral phosphines. So we can add that chiral phosphine to our substrate, and further uh, as like chiral auxiliary method, we can do the stereoselective carbon bond formation by using this phosphine based catalysis. The another type is the enolate and dienolate catalysis. So this enolate dienolate catalysis is not much trivial, but this is also we can search for that. This is also one of the asymmetric activation mode, uh, and in which the you can do the stereoselective carbon bond formation. Further, acylium as well as the N heterocyclic carbines, further C2 enolate catalysis, then C3 enolate, followed by the SOMO catalysis. The example of the SOMO catalyst probably we have professor has already covered. And if you look at the non-covalent activation mode, in that one they did the Bronsted catalysis, further the phase transfer catalysis, and the chiral anion as well as the hydrogen bonding catalysis. So these are the some activation modes, that is the covalent and non-covalent. Just superficially that we have go through all these modes. Further, as we have seen earlier, that is the in this type of iminium we have already seen. Now this is the enamine based catalysis in which we can add the enamine. Uh, the addition takes place in the stereochemical fashion. So if you have some such chiral group around this enamine, uh, this are whether it is directing the beta or alpha, this further addition of this electrophile takes place in the same manner. So in this way, so the driving force for this reaction is the lone pair of electron. So this lone pair get involved here, and it attacks to the bond. So at this position the next upcoming electrophile getting added. So this is the example can form the acyl or alkyl. We can do acylation or alkylation. This is also the same alkylation reaction. Further, we can also do the, if you have such electrophile, this is the 1,4 addition we can do. This 1,4 addition is works goes through Michael addition. Why we call it as a Michael addition? So we know generally aware about the addition takes place on such system. Here, it will be a Michael addition. We generally the addition takes place at the 1,4 position. So we refer as a Michael addition. So we can able to add, and depends upon the stereochemistry of this bond. So in this case, so if you have such a kind of a chiral group here, whether it is directing upward or whether it is directing uh, downward, or here as well. We can, it may be here, 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 any places. It drives some sort of uh, stereochemical control in the reaction, and the addition of the further electrophile will take place in the same, in that manner. So the stereochemistry of this bond is getting defined. These bonds is getting defined by the stereochemistry of the steric group present, the stereochemistry of the group present in the imine part, or the that is, or the stereochemistry of present in the enamine. So this is the, we have already, it's not much to discuss in this case. So this is the alpha functionalization of the aldehyde and ketone, that in the same manner that discussed earlier. So just the abstract formation of the imine, and again the addition of the electrophile, it gives the product. And also the stereochemistry that also we have discussed depends upon the stereochemistry of side group present. So as of now, what we have discussed in this lecture, so we have seen, although the alkyl methylation looks quite straightforward, but that's not the case, because if you just want to simply perform the monomethylation, uh, so there are different catalysts that we need to use. That is, the we have seen the MnCl2 based catalyst, or MnBr2 addition of this additive that can control. Further, we have seen the different type of thermodynamic control and kinetic control, how these affect the formation of enolates, and subsequently the formation of the product. The further, we have seen, if you want to perform a selectively monomethylation, and how the protocol that we need to follow. So this the, if you want to perform the selectively monomethylation, so in that case, these many number of steps are involved. So although the reaction looks simple, so the just only the formation of the keto to the alpha methyl keto, although reaction looks simple, but still we need to follow a long protocol, which is the first step is the activation, addition of the C-double-bond-OET, the information of the carbon methyl bond, and again the deprotection of this C-double-bond-OET group, and it gives the formation of the product. Uh, and this is why this is required, that also we have seen. So if you perform such reaction, and these many number of products are getting formed, which is like monomethylation, dimethylation at the two different sites, also the dimethylation, sorry, the trimethylation and the tetramethylation. These many number of products are getting formed if you want to perform the reaction just by adding the base. Further, we can able to add the phase transfer catalyst that can help to get the thermodynamically stable product. So in this case, so we have added the PHCH2 C-double-bond CH3, that's the ketone, and by adding this phase transfer catalyst, that is the tetrabutyl ammonium bromide, and just simple base like KOH, it gives the thermodynamically controlled product formation in the about 100%. So this protocol is also one of the good protocol to form a thermodynamic control product. Further, we have seen the chiral involve some examples which involve the chiral bond formation, and these are the examples of the some regioselective control product. So by adding this condition, we can able to get the thermodynamically controlled product, which is in the 97%. But just if you just change the base, then we get the kinetically controlled product, which is in the 99%. So just by varying the base, we can able to control whether it is thermodynamic or the kinetics. And also important to note, this reaction is at the room temperature, and the kinetically controlled reaction with the LDA, which is occurs at the minus 78 control 78 degrees Celsius. If you perform this reaction at the room temperature, then the selectivity get vanished, and we will not get this exhaustive selective sorry, the selective formation of the kinetically controlled product. So, and also we have seen some examples of these which involve the cyclization, sorry, the bond formation, which is in the stereochem control manner. So not, this is not the example of stereo control, this is example of the regio selective reactions. So this is the formation of, we have seen example with the mes mesembryne formation by using such carbon bond formation. And yeah, these are some example that are discussed. This is the examples which involve the use of the chiral auxiliary, how this chiral auxiliary can control the formation of the new bond in the chiral fashion. So we can add the chiral auxiliary to our molecule and we perform the reaction. And last step, we have to you like LiBH4. If you use the LiBH4, this entire chiral auxiliary get converted uh, and followed by again this kind of reducing agent which can cleave this carbon, this amide bond formation. So this is the example that also we have seen. Just if you want to do the stereochemical, if you want to convert this product into this one, just formation of the carbon methyl bond in the stereochemical manner. So how many steps are involved? First step was the addition of the chiral auxiliary. So we have added the chiral auxiliary across this bond. So first we have to do the oxidation followed by the addition of the chiral auxiliary. So once we have added the chiral auxiliary, then we perform the our reaction in the stereochemically controlled, which is driven by the stereochemistry in the chiral auxiliary, right? So that's the second step. And further, once we get the stereochemical control bond formation, then it's time to remove the our chiral auxiliary. So we have performed the simple reaction. In this case was the addition of LiBH4. So it reduces the it deprotect these amides. It gives the aldehyde, and again the subsequent reaction gives the aldehyde converted into the alcohol, right? So we get a final product. So the three major steps involve addition of chiral auxiliary, then the performing our addition reaction in the stereochemical manner, and further removal of the chiral auxiliary to get the desired product with the required stereochemistry. So these are the some examples, and I hope all these examples are good enough to understand the use of chiral auxiliary, also the use of imine catalysis. Yeah. So if you have any doubt, please let me know, or we'll stop here for today. That we can see some more example in the next video. We'll stop here for today, and thank you for joining.